Welcome to the deep dive. Today we're getting right into the nuts and bolts, literally, of aviation maintenance.
Sounds good.
We're focusing on common hand tools and measuring devices, drawing on those resources you shared with us.
That's right. It's a really core area for any AMT.
Our goal is, well, to go beyond just identifying these tools. We want to really understand their critical functions, the right way to use them, and why they're just absolutely indispensable for keeping aircraft safe and, well, in the air.
It truly is a vast world,
Yeah.
Inside an AMT's toolkit, as you mentioned, the sheer complexity of modern aircraft, it really dictates the range of specialized tools you need.
Right.
I mean, the needs for maintaining a huge commercial airliner are just vastly different from, say, a small Cessna. And you see that difference right in the tools.
Exactly. And while we're going to cover a broad spectrum of these essential tools, it's really crucial to remember this discussion isn't it's not a substitute for real hands-on training and good judgment.
Absolutely not.
The materials you sent even touch on how important ingenuity and resourcefulness are in this field. It's not always just following steps, is it? Sometimes you need to think creatively.
That's a vital point, yeah.
Yeah.
While sticking to procedures and using the right tools is, well, paramount, that ability to adapt and problem solve, that's really the mark of an experienced tech.
Mm-hmm.
And across all these tools, no matter what you're holding, the info consistently points back to the basics: safety, meticulous tool care, and proper storage. They're the foundations, really.
Okay, let's dig in then. Starting with some real workhorses, hammers and mallets.
Right.
The information highlights that metal head hammers are classified simply by the weight of the head. Makes sense.
Pretty straightforward, yeah.
But then we get these soft face hammers: wood, brass, lead, even plastic.
Yeah.
What's the main reason for having those?
Well, the critical thing to understand is their purpose.
Mm-hmm.
Delivering force without damaging the underlying material. You use these softer faces when you're, say, forming soft metals or tapping on delicate surfaces that a steel hammer would just wreck. And the sources are really clear. You absolutely shouldn't use them for hitting things like punch heads or bolts or nails. That kind of impact just deforms the soft face super quickly.
Right, ruins the tool and probably doesn't do the job properly either.
Exactly. You lose that controlled force delivery.
So it's about controlled impact. Then we have mallets: hickory, rawhide, rubber. These seem like they're for even finer work, like shaping thin metal without leaving sharp dents.
Yeah, that's the idea. Mallets tend to distribute the force over a slightly broader area, so you get a more gentle shaping action. And it's interesting, the sources specifically call out using wooden mallets with wood chisels or gouges.
Why is that?
Prevents damaging the chisel handle. Keeps it intact longer, Makes sense. So when we're using any of these metal hammer, soft-faced mallet, what are the absolute must-do best practices?
The material stresses a few key things. First, always pick the right tool for that specific job. Don't just grab any hammer.
Okay.
Always check the handles tight. A loose hammerhead is a serious hazard.
Yeah, I can imagine.
And when you swing, think of your forearm as an extension of the handle. Swing from the elbow, not just your wrist.
Right, more control.
And aim to strike squarely, using the whole face. And this is huge, especially metal-on-metal safety glasses. Non-negotiable.
Definitely. Flying debris is no joke.
Absolutely.
Yeah.
And finally, keep those striking faces smooth. No dents, no chips. Those imperfections can transfer right onto your workpiece.
Got it. Fundamental good practice. Okay, let's move to another category everyone uses: screwdrivers.
Ubiquitous.
Classified by shape, blade type, length, but fundamentally, what's their one job?
Simple, really. Apply torque to loosen or tighten screws or screw head bolts. That's it.
And a crucial point the info brings up right away is selecting the largest common screwdriver that properly fits the slot. Like, at least 75% contact. Why so specific?
Because using the wrong size, especially one that's too small, leads to a whole mess of problems.
Like what?
Well, you can damage or burr the screw slot, making it hard or impossible to turn. You might even need a screw extractor then, which is a real pain.
Ugh, yeah, been there.
And if it doesn't fit well, it's way more likely to slip. And when it slips, bang, you damage adjacent parts. Not good on an aircraft.
Definitely not. So, standard slotted screwdrivers are just for slotted heads, like those camlock fasteners on cowlings.
Perfect example. That's exactly what they're for. Now, recessed heads, that's where things get a bit more nuanced. Phillips and Reed and Prince.
Ah, yes. This is a distinction I suspect many people, myself included, sometimes overlook. Tell us about that.
Well, it's subtle, but really important. The Reed and Prince head forms a perfect pointed cross, right down to the center. The matching screwdriver has a sharp, pointed tip.
Okay.
The Phillips, though, has a slightly blunter, more rounded center in the cross. And the Phillips screwdriver tip reflects that it's not as pointed.
So they look similar, but they're not the same.
Not at all. And here's the critical bit.
Yeah.
They're not interchangeable.
Sure.
Using a Phillips on a read and print or vice versa, choose up both the screwdriver tip and the screw head.
Right. You'll cam out, strip the head.
Exactly. Makes removal incredibly difficult. The sources even mention common sizes, like number 1 and 2 Phillips, and their matching screws. Using the wrong one is just asking for trouble.
That's genuinely useful. I'll definitely pay more attention now. The material also mentions offset screwdrivers. When would an AMT reach for one of those?
Oh, they're lifesavers when you've got almost no vertical space. Those 90-degree bends let you get at screws tucked away where a straight driver just won't fit.
Tight spots.
Exactly. And they come in both standard slotted and recessed head types, so they're pretty versatile for those awkward jobs. The ratcheting right angle ones are even better in really confined spaces.
And just as vital as knowing how to use them is knowing what not to do. What are the big don'ts for screwdrivers?
The sources are very clear. Don't use them for chiseling or prying. That side force can bend or snap the blade easily.
Makes sense.
And absolutely never use one to check electrical circuits. Huge risk of arching. You can burn the tip, sure, but worse, you could fuse the blade to something or cause a short circuit. Very dangerous.
Yeah. Sounds like a recipe for disaster. What about safety when working with small parts?
Always secure the part. Put it in a vise. Clamp it to the bench. Never, ever hold a small part in your hand while trying to turn a screw in it. If the screwdriver slips.
Ouch. Yeah, nasty puncture wound waiting to happen.
Precisely.
We also see these replaceable tip screwdrivers, the 10-in-1 kind of thing. What's the appeal there?
Mostly convenience and versatility. You get a bunch of different tips, flat, Phillips, read and prints, Torx, square drive, whatever, all in one handle. Fewer tools to carry, maybe cheaper in the long run too.
And finally, power screwdrivers seem like a time saver, especially with lots of screws, but there are caveats, right?
Absolutely. Cordless power screwdrivers are great for removing lots of screws quickly. But for installing, got to be careful with that slip clutch setting.
How so?
Set it too high, and you strip the screw head before you know it. The advice is always to start screws by hand first. Get them properly aligned, avoid cross-threading.
Which can really weaken the joint.
Exactly. And a really critical point. The material warns against using cordless power drills with screwdriver bits for screws. They usually lack a sensitive slip clutch. Much higher risk of damage.
That's a really important distinction. Okay, let's shift to another essential group. Pliers and plier-type cutting tools. Looks like 3 main types pop up frequently in aviation maintenance.
Indeed. The sources point to diagonal pliers, needle nose, and duckbill pliers as the most common. Usually sized by overall length, maybe 5 to 12 inches. Round nose pliers get a mention too for things like crimping soft metal, but they warn against heavy work you can spring the jaws.
Needle nose, those long, skinny jaws seem obvious for tight spots, right? Holding small things.
Yes, exactly. Getting into confined spaces, holding tiny parts, making small adjustments. Very useful.
And duckbill pliers. That name paints a picture.
It does. They have thin, flat jaws, kind of like a duck's bill, and their main job in aviation is pretty specific. Twisting safety wire.
Ah, safety wire. Fundamental stuff.
Absolutely. Keeps fasteners from vibrating loose. Duckbills are the go-to for getting that wire twisted just right.
Then diagonals, often called dikes. Sounds like the cutting specialists.
That's right. Short jaws, angled cutting blades, great for snipping wire, rivets, small screws, cotter pins, and, as the info notes, also essential for safety wiring, both installing and removing it.
So duckbills and diagonals are the safety wiring dream team, basically.
Pretty much, yeah. You'll see them used constantly for that.
Now, with all these pliers, any big rules of thumb for using them correctly?
2 crucial ones stand out. First, don't try to make them do more than they're designed for, especially the long-nosed types. They can be a bit delicate. Overload them, and you can spring the jaws, break them, or nick the edges, making them useless.
Okay, respect their limits. What's the second rule?
Never, ever use pliers to turn nuts or bolt.
Why not? Seems tempting sometimes.
Because the jaws aren't shaped for that. They slip, they round off the corners of the nut or bolt head really fast, and then you're stuck trying to get it off with the right tool, which might not even grip anymore. Big no-no.
Got it. Use a wrench for wrench's work. Okay, let's punch things up. Moving on to punches, sounds like they do more than just make marks.
They're surprisingly versatile, yeah. Used for locating centers for drilling, starting pilot holes, punching holes in thin sheet metal, transferring hole locations from templates, and also for removing damaged rivets, pins, or bolts.
Two main types mentioned, solid and hollow, and solid ones are classified by point shape.
That's the general breakdown. Let's look at the solid ones first. Prick punches come up first. What are they for?
Prick punches are for making small, shallow marks on metal, often used with, say, a paper template to transfer marks onto the workpiece. Just light taps with a hammer.
Light taps being key, right?
Absolutely. Heavy blows can bend that fine point or just mess up the metal unnecessarily. Okay. Then center punches. How are they different?
Center punches make a bigger, deeper indentation. Specifically, the kind you need to accurately start a twist drill bit, stop it from walking across the surface.
Ah, the dreaded drill walk.
Exactly. Center punches help prevent that. But again, don't whack it too hard. You can dimple the metal or even cause a bulge on the other side of thin sheets. They're generally heavier than prick punches and have that typical 60-degree point.
Drive punches or tapered punches? Name suggests their use.
Right on. Used to physically drive things out, damaged rivets, stubborn pins, seized bolts. They have a flat face, not a point, and are sized by that face width. The taper helps sometimes with starting.
And pin punches or drift punches. Sounds similar to drive punches. What's the difference?
Very similar purpose, yeah. Driving out pins and bolts. The main difference is the shank. Drive punches usually taper down towards the face. Pin punches have a straight shank, same diameter all the way to the face.
So you'd maybe start with the drive punch, then finish with a pin punch?
That's a common technique, exactly. Start with the drive punch to get it moving. Once the taper might bind, switch to the right diameter pin punch to push it all the way through without damaging the hole.
Any tricks for really stubborn ones?
The info mentions using a small piece of scrap, soft metal, copper, brass, aluminum between the punch and the pin. Helps cushion the blow, prevents mangling the pin itself.
That's a good tip. So based on this, using a prick or center punch to actually remove something. Bad idea.
Terrible idea. Their points will just spread the material or cause it to bind even tighter. Makes removal harder and risks damaging the parts.
Okay. Last one here. Transfer punches for templates.
Precisely. They're about 4 inches long, usually. The point tapers then go straight for a bit, designed to fit snugly into guide holes in a template. The very tip is like a prick punch, used to accurately transfer hole locations from the template to your material.
Gotcha. All right. Moving to a huge category, wrenches. Open end, box end, socket, adjustable, ratcheting, plus all the special ones like Allen wrenches. Good thing they're often made of that tough chrome vanadium steel.
Yeah, they need to be durable. Let's start with open end. Solid, non-adjustable, parallel jaws, often angled.
Yep. That angle, usually 15 degrees, helps you get into tighter spots, gives you a better swing arc. Basic job. Grip nuts and bolts for turning. Box end wrenches seem really popular, especially for tight quarters. What's their big advantage?
They completely surround or box the nut or bolt head. Gives a much better grip, less chance of slipping and rounding the corners.
And most are 12-point, right?
Yeah, that 12-point design is key. It means you only need a small swing, like 15 degrees, to get a new grip on the fastener. You can even flip the wrench over in really tight spots to get an even smaller effective swing.
But the sources say they can be slower for fully removing a fastener.
That's the trade-off. Unless you can swing it all the way around, you're constantly lifting and repositioning it. Slows things down once the nut is loose.
Which is where the open end is faster for just spinning it off.
Exactly. Which leads us neatly to combination wrenches.
Best of both worlds, right? Box end for breaking loose or final tightening. Open end of the same size on the other side for speed.
Seems like a really practical design. And ratcheting box ends are another option for speed, too.
Yeah, swing back and forth without lifting. Saves time, especially on long bolts. Now, socket wrench is the two-part system.
Right. You've got the socket itself, which fits the fastener, and then the handle that drives it. The big win here is modularity.
So many handles. T-handles, ratchets, speed handles.
Plus, extensions, universal joints. You can build a setup to reach almost anything. The socket clicks onto a square drive on the handle, usually held by a little spring-loaded ball of poppet.
Adjustable wrenches. The one-size-fits-most tool.
Kind of the utility player, yeah.
Yeah.
Smooth jaws, one fixed, one moved by a screw. Handy in a pinch, but the info stresses they're not a true substitute for fixed wrenches.
Why the caution?
They're just not as secure. You have to be careful to pull on the fixed jaw side to minimize stress on the movable jaw. And you really need to snug it up tight on the fastener, otherwise it's very easy to slip around the corners.
Okay, use with care. Now, the special wrenches, this is where things get really specific.
Exactly. Tools for very particular jobs, like crowfoot wrenches, look like an open-end wrench head on a square drive adapter. For nuts you just can't reach otherwise.
And flare nut wrenches for fluid lines.
Yep, critical in aviation. They look like a box-end wrench, but with a slot cut out, so you can slip it over the tubing onto the B-nut fitting on fuel, hydraulic, or oxygen lines.
That slot is key.
Absolutely. And like crowfoot wrenches, they often have that square drive, so you can attach a torque wrench. Really important for getting those line fittings tightened correctly.
We also see spanner wrenches mentioned: hook, pin, face pin.
All for dealing with round nuts that have notches or holes. Hook spanners grab notches on the outside. Pin spanners use a pin that fits into a hole on the face or edge. Different types for different nut designs.
Allen wrenches, we know those. For hex socket screws.
Right. Those L-shaped X keys, or bits for ratchets, standard tool for Allen screws and bolts, come in lots of sizes.
And then a really critical one, torque wrenches. All about precision force.
Absolutely essential. They measure the twisting force, the torque you apply to a fastener. So critical for aircraft integrity.
And they need careful handling and checking?
Definitely. Treat them like measuring instruments.
Yeah.
Inspect before each, use bent pointer, cracked dial, look dropped. If anything seems off, it needs testing. And regular calibration is mandatory. You have to know it's accurate.
How often is calibration needed?
Depends on the wrench and usage, but schedules like every 6 or 12 months are common. You have to follow the maintenance schedule.
3 main types mentioned: deflecting beam, dial indicating, and micrometer setting.
Right. The beam and dial types you read visually as you apply force. The micrometer type, you preset the torque, and it clicks or breaks over when you reach it. Very common now. The sources mentioned Chapter 7 for more detail on using them.
Strap wrenches also pop up under special, delicate stuff.
Yeah, really useful for things like tubing, pipes, fittings, especially on lighter aircraft where components might be easily damaged. The fabric or plastic strap grips without scratching or crushing like pliers might.
And impact drivers for the really stubborn fasteners.
Exactly. You hit it with a mallet, and an internal cam converts that impact into a sharp rotational jolt. Great for breaking loose seized screws. But you must use impact-rated bits and sockets with them. Regular ones can shatter.
Good warning. Okay, cutting tools. Hand snips first, different types for different cuts.
Seems so. Straight snips for straight lines and gentle curves. Curved snips for tighter curves. Hawk's bill for intricate shapes. And aviation snips.
Those sound heavy-duty for aluminum alloys and stainless steel.
Exactly. They're designed for the tougher materials found in aircraft. They often have compound leverage handles for more cutting power, up to about 0.051-inch thick material. And they come in right and left cutting versions to make following curves easier.
Interesting distinction made between snips and hacksaws. Snips don't remove material. Practical implication.
It means the cut edge from snips might have tiny fractures or be slightly distorted. So the recommendation is to cut about 130 seconds of an inch outside your line with snips, then file down to the line for a clean, undamaged edge.
Makes sense. Hacksaws then. Blade, frame, handle. Pretty standard setup.
Yep. Key thing is mounting the blade with teeth pointing forward, away from the handle. Cutting happens on the push stroke.
Blades come in different materials and pitches, right? Teeth per inch.
Yeah. All hard blades for solid, tough stuff. Flexible blades, with just the teeth hardened, are better for hollow or thin sections, less likely to break. And the pitch teeth per inch matters. Coarse pitch, like 14 or 18 ppi, for softer, thicker materials. Finer pitch, 24 or 32 TPI, for harder or thinner stuff, keeps more teeth engaged.
So using a hacksaw properly, what's procedure?
Select the right blade, mount it teeth forward, tension it correctly, not floppy, not banjo tight. Clamp your work securely. Maybe nick the start point with a file to guide the blade.
Good tip.
Start the cut with light pressure just outside your line. Keep at least 2 teeth on the work. Use steady forward strokes, lifting slightly or relieving pressure on the backstroke. Use the full blade length, maybe 40-50 strokes a minute. Consistent pressure.
And afterwards?
Clean up chips. Loosen the blade tension for storage.
Chisels next. Hard steel, cutting softer metals. Used for shearing rivets, splitting nuts.
Yeah, especially in tight spots. Sized by cutting edge width. You've got flat cold chisels for general work, cape chisels for square corners, round nose for grooves and fillets, diamond point for V-grooves. Hold firmly, strike squarely with a ball peen hammer.
Files, huge variety. What are they used for generally?
Squaring ends, rounding corners, removing burrs, smoothing edges, filing holes. Lots of shaping and finishing tasks. Key things are length, kind, Coarseness and cut, single or double.
Single cut versus double cut.
Single cut has one set of parallel teeth, usually for a smoother finish. Double cut has two sets crossing each other, removes material faster but leaves a rougher surface. Coarseness ranges from rough down to dead smooth for fine finishing.
So many shapes, too flat, hand, mill, square, round, triangular, half round, even special ones like vixen or curved tooth.
Exactly. Each shape is suited for different contours or tasks. Hand files often have a safe edge with no teeth for working in corners. Mill files are often single cut, good for draw filing. Vixen files have curved teeth for rapid work on soft metals or wood. Choosing the right shape and cut is crucial.
And using them correctly. Cross-filing, draw filing.
Cross-filing is the basic back and forth motion, pressure on the forward stroke. Draw filing is holding it at both ends and moving it sideways along the work. Gives a very smooth finish. Always use a handle for control and safety. Relieve pressure on the return stroke.
Care is important too, right? Keep them clean and dry.
Absolutely. Store them so they don't bang together. Keep them dry, rust dulls them fast. And clean them often with a file card or wire brush to remove pin filings. A clogged file doesn't cut well.
Okay, making holes, drills. Hand drills, breast drills, electric, pneumatic. Pneumatic preferred around flammables.
Big safety point, yeah. No sparks from pneumatic tools. Twist drills are the standard bit hardened steel cylinder with spiral flutes and a cutting point.
Materials, carbon steel, high-speed steel.
Carbon steel for general work, cheaper. High-speed steel, HSS, for tougher materials, lasts longer. Most have two flutes.
Sizing seems complicated. Fractions, letters, numbers.
It is a bit. Fractional sizes are common, like 14-inch. Letter sizes, AZ, and number sizes, AD down to 1, offer finer increments. You often need a chart to convert them or know the specific size needed. Standard point angle is 118 degrees, but sharper for soft metals.
Sharpening them seems key. Requires practice.
Definitely. Need to get both cutting lips the same length and the correct 59-degree angle on each side for 118 total. Use a grinder carefully, check with a gauge. There are special jigs and grinders that help too. A dull drill is inefficient and can make oversized or rough holes.
Reamers. Used after drilling.
Yes, to smooth and enlarge a hole to a very precise final size. You have to drill the hole slightly undersized first, maybe 0.000 to 0.0007 inches smaller.
Why undersize?
Reamers aren't meant to remove a lot of material. Trying to take too much can overload and damage them. They're brittle, so handle with care. Always turn only in the cutting direction, never turn backwards.
Straight flute versus spiral flute.
Spiral flutes tend to chatter less, give a smoother finish, but straight are often cheaper. Both usually have a slight taper to help start them in the hole.
Countersinks. For making fastener heads sit flush.
Exactly. Cuts a cone-shaped depression. The angle has to match the fastener head, like 100 degrees is common. Special stop countersinks let you control the depth precisely, sometimes with micrometer adjustments. Don't remove too much material, weakens the joint.
Taps and dies for threading.
Yep. Taps cut internal threads in holes, dies cut external threads on rods, hardened steel, precision ground. Common thread types are national coarse, fine, extra fine, pipe.
Hand taps usually come in sets of 3.
Taper, plug, and bottoming. Taper starts the thread easily. Plug cuts further down. Bottoming goes almost all the way to the bottom of a blind hole. Dies can be adjustable or plain. Use the right tap wrench or die stock to turn them.
Final category, layout and measuring tools. Precision instrument.
Absolutely critical. Handle with extreme care. Accuracy of the whole job depends on them. No dropping, bending, scratching.
Rules or scales. Steel, rigid, or flexible. Inch units, common in aviation.
Right. Divided into fractions or decimals. Can measure or just be used as a straight edge.
Combination sets seem really versatile. Square head, center head, protractor head.
Super useful. The square head acts like a tri-square, has a level, can be a depth or height gauge. Center head finds the center of round stock. Protractor head sets and checks angles. All slide on a grooved rule.
Scribers. Metalworking pencils.
Good analogy. Sharp steel point for marking lines on metal. Keep the point sharp, hold it like a pencil, keep it close to your straight edge. Scribed lines should be visible but shallow. Only used for lines to be cut, scribes can cause stress risers.
Dividers and pencil compasses. Arcs, circles, transferring measurements.
Pencil compass has a pencil leg for drawing. Dividers have two sharp points, mainly for transferring measurements accurately or stepping off distances. Use lightly on metal to avoid scratches unless the mark will be removed.
Calipers inside, outside, hermaphrodite.
Outside measures external diameters. Inside measures internal diameters. Hermaphrodite has one caliper leg and one scriber leg, used mostly as a marking gauge, not for high precision.
And then micrometers for much higher accuracy.
Way more accurate than rules or basic calipers. Measure down to thousandths 0.0001, or even 10 thousandths, 0.0001 of an inch. Outside mics are most common for AMTs, shafts, sheet metal thickness, etc. Need to convert fractions to decimals sometimes.
Reading them, barrel and thimble scales.
Takes practice, but it's logical. The barrel shows tenths and 0.025 inch increments. The thimble shows thousandths, 0.001. You add the readings together, read the last full tenth mark visible, add the number of 0.025 marks past it, then add the thimble reading lined up with the barrel's index line.
The vernier scale adds another digit.
Exactly. It allows reading to 10 thousandths, 0.0001. You find which vernier line on the barrel aligns perfectly with the thimble line and add that value. Need good eyes or magnification sometimes.
Using them correctly is vital, too. Don't over-tighten. Keep calibrated.
Absolutely. Gentle handling. Don't force the spindle. Use the ratchet or friction thimble. Keep them clean. Check calibration regularly with gauge blocks or standards.
Dial indicators measure small variations like shaft runout.
Yep. Probe touches the surface. Dial shows tiny movements in thousandths. Use for runout. Checking flatness like brake disc warp. Must be mounted rigidly so the indicator doesn't move.
And slide calipers, more accurate than a ruler, less than a mic?
Generally, yes. Good for quick inside-outside depth measurements with reasonable precision, often using a vernier scale or digital readout.
Wow, okay. We have definitely covered a huge amount of ground on hand tools and measuring devices. It's so clear how fundamental these are.
Absolutely fundamental. Selecting the right tool, using it correctly, taking care of it. It's non-negotiable for safety and quality in aviation maintenance. It's that mix, like the sources said, of following procedures but also having that ingenuity when needed.
It really is. This has been incredibly insightful, thinking about how critical these seemingly simple tools are for keeping complex machines flying safely. What aspect of their design or application strikes you as most, I don't know, surprisingly intricate or vital? It's definitely something to think about. Thanks for joining us on this deep dive.